It's great to have Idan speaking today, Idan Attias. Idan is an ideal postdoc in both senses of the word. He's hosted jointly by Lev Raisin at UIC and by Nati and me here at TTIC. Idan works in foundations of machine learning and data-driven sequential decision-making with connections to game theory, private data analysis, optimization, information theory, and theoretical computer science. Among other things, Idan received the Best Paper Award at ICML 2024 for his work on the information complexity of stochastic convex optimization. And today he's going to be talking about multi-arm bandits. So take it away.
Thank you, Avram. So I will be talking today about two papers on multi-arm bandits. The first one is about adaptivity to causal structure, made in ICML 2024. The second one is about online learning with delays and constraints. Will be presented next month. Sorry for those of you that heard the second part of the talk on Monday. This is joint work with wonderful students. Z is a PhD student at the University of Toronto and Vector Institute. Alex was an undergrad once we worked on this paper. This is really impressive. He led the paper, really original idea. And Dan Roy is a faculty. And I've spent some time, I visited Dan for 4 months and we had some productive time. Previous time I presented a paper on memorization and privacy for over-parameterized models. Today I'm going to present something completely different that Dan got me really excited about. So it's about, first paper is going to be about adaptivity. The title of the paper was Causal Bandits, the Pareto Optimal Frontier of Adaptivity, a reduction to linear bandits and limitations around unknown marginals. Okay, so what is adaptive algorithms and sequential prediction? So in statistics, we used to usually make assumptions to develop some statistical methods. Sometimes these assumptions are false or unverifiable. At the same time, in computer science, we've typically focused, for the most part, on the worst case scenario, which is great if we can get good guarantees for the worst case scenario. But yet, we expect that if we have a setting that is nice or easy, then we can expect a better performance. Okay, so what adaptivity means is that simultaneously we want to benefit from assumptions when they hold. If they don't hold, we want to perform as well as possible as if they fail. It's a worst case guarantee. And we don't know in advance in which world we're in. Okay? The typical example is stochastic environments versus adversarial environments. Usually in stochastic environments, we can get better rates. So in some sense, I'm really excited about this topic because you develop a meta-algorithm and it adapts to the structure of the problem and gives you the best you can hope for in some sense. So there has been a lot of work in this topic. There are many names for this type of results. One of them is best of both worlds. Some people are talking about instance optimality, model selection. There are many names for that. I chose best of both worlds. I think it's the best one for this context. So in multi-arm bandits, there was a really nice paper by Sebastian Bubek and Alexander Slivkins, where they showed that you can do that in bandits. You can do best of both worlds in stochastic and adversarial bandits. And since then, there were many papers about this type of results in bandits. One really cool result is by Zimmert and Seldin. They're using a regularizer that is called the Tsallis entropy. Magically, this regularizer works really well in many, many algorithms. And it has been used since then. I've seen this Tsallis entropy at least in 50 or more papers. And Dravi is in the Dravi used the Tsallis entropy for developing criteria for decision trees, unifying many, many criteria from the past. Got the best student paper over the TUAI. It's a beautiful idea. So pay attention to this Tallis entropy. It seems like a really powerful idea. And there has been also many papers in online learning where we have full information. Really, really nice papers. There has been also many papers in reinforcement learning. And more broadly, there is this beautiful by Tim Roughgarden about beyond the worst case analysis of algorithms in T6. So this is not just learning, it's like more broadly. And the idea in this paper is that we want to study adaptivity to causal structure in the framework of multi-arm bandits. By the way, please ask questions, okay? Okay, so let's motivate multi-arm bandits with clinical trials. So let's say I have a set of drugs, you can call them arms or actions, and I have a stream of patients, and I want to find the best treatment, the best drug as fast as possible with minimal harm during the process. And there are many applications for that, pricing, recommendation systems, A/B testing, and so on. And since we have only a bandit feedback, we don't know what would have happened had we taken a different drug. We gave a shot. We're going to see the result only for this shot. So there is a trade-off between exploration, keep trying new actions in order to understand how they perform, and exploitation, playing so far the arm that we believe that gives us the best payoff. Okay, so in this paper we're going to discuss a model of multi-arm bandits with post-action measurements. So imagine that we have many possible treatments, a huge number of treatments, but we have some domain expert that tells us, in the end of the day, take some measurements, and only by these measurements you can know if this drug is effective or not. Like you can have maybe thousands of drugs, but only certain measurements after you give the drug actually determine whether it was effective or not. So I'm not an expert in this topic. There are many examples, but I took the example of diabetes. Maybe a post-treatment measurement could be a blood sugar level. And if it's above a certain threshold, then it could be a good predictor if it was a good treatment or not. So why is it good? Because maybe this measurement is really a binary signal, and it's a low-dimensional predictor. And maybe we can adapt to this structure. Okay? We can find the best drug much faster just by using these measurements.
When you say predictor, so should I be thinking of this as getting the label information? Did it work or not? Or should I think of this as somehow a predictor of which arm I should play?
So what happens is, in the standard multi-arm bandits, I'm taking an action, I see a reward. Here I'm going to see a reward. In another context, I'm going to see the measurement. Okay, I'm going to have a distribution, the product distribution on the post-action context and the reward. And I want to use, if this post-action context is useful, I want to use that for designing the algorithm. Does it make sense?
So this is something that's affected by the choice? In other words, it's not like...
It's a function of the action.
Okay, so it's not like you could use this and then use that first to decide whether... Do the measurement first.
It's true. It's not contextual bandit. In contextual bandit, you see the context in advance. It represents the patient. Here, it's a function of the action. You gave someone the drug, and you see the measurement.
So it's in addition to so it's not the same thing as the payoff. It's a set, but it's related.
It's a great question. Yeah.
Okay.
Yeah.
So can you model this as an MDP with Horizon 2, where you transit to another state after you action?
So we're doing bandits. I think there are papers also about reinforcement learning, but no, you're going to see in a second. It's just you can model it with bandits. Just instead of just seeing a reward, we're going to see another information. So usually in stochastic bandits, you push the action, then you see the reward. Now you're going to see the reward and another variable. You're going to have a product distribution on these two. And if it is useful, we want to do better. If it's not useful, we want to recover the worst case guarantee. And we're going to formalize it. Does it make sense? Yes.
So So do we know the post-action measurement of function here? Or is it directly related to the payoff, or is it?
So it's every action. Maybe I'm gonna just show that. When I push, okay, I have a distribution. Every action has a distribution over the post-action context and the reward. So so for sure, yeah, it might be if it's correlated with the reward, I can do maybe better. Yeah, it should have. If I want to exploit the structure, it should have said something about that.
So, what is the relationship with this setting and partial monitoring setting?
I'm not an expert in partial monitoring, but
so basically in partial monitoring, right? So you had a kind of observation that is different from the payoff, and then you learn the mapping between the observation and the actual payoffs, and to optimize. So you don't see the payoff, you only see the observation, and then you.
So we were going to see the payoff and the observation.
And here, oh, you see both?
Yeah, you're going to see both the reward and the measurement. So maybe that's...
Yeah.
Okay. Okay, so let's formalize stochastic multi-arm bandits. We have a set of arms and T rounds. The horizon is T. The adversary environment picks a set of distribution indexed by actions. So for each action, there is a distribution. Over the distribution is, we can think about it as reward or loss. I'm going to think about it as loss. Then for each round T, the learner takes an action. The environment responds by generating the loss from the relevant distribution. The learner observes the loss and updates the method for future rounds. Bandit feedback, we don't observe the counterfactual. We don't know what would have happened if we taken a different action. The goal is to identify the optimal action, do it quickly, and as harmless as possible during the process. Once we try bad drugs, we might harm people. Okay, so we want to minimize that. And the objective is to minimize the expected regret. We have a regret minimization algorithm if this term is going to be sublinear in T. And what is the regret? Is roughly the cumulative loss by the actions of the learner compared to the best fixed action in hindsight, and we take expectations. So it's the pseudo regret, but this is our objective. Another thing we could do is ask for best arm identification. There is a related setting that actually the causal bandit setting was introduced for the other setting, which is best arm identification, where we don't care what happens during the process. We just care that by the end of the process, we're going to find the best arm. So think about it as some people sacrifice themselves for science. I was like, okay, 10,000 people. I was like, do whatever you want to me. I don't care what's going to happen in the process. Then I will use them in order to identify the best treatment. This is pure exploration setting. It's best arm identification. And actually, the setup that we'll see was introduced for this problem. But then it was extended to the benchmark of cumulative regret, where I actually care about what's going to happen during the process. Okay, so now we're gonna discuss stochastic bandits with post-action context. It was introduced in 2016, and last time I checked, it had already more than 300 citations. So it's pretty hot topic, not just bandits, but sequential decision making with causal inference. It's pretty active area. So okay, so in red is the change. We have also a universe of post-action contexts. Now each distribution is indexed by A is a distribution over the context and the reward. Now when the adversary generates a loss, we observe also the post-action context. So we gave a treatment and also we get the measurement. And then the learner observes these two and update the learning algorithm. Okay, so this is the change. If you like this formulation if it makes sense. Okay. So, as we've said, I want to adapt if it helps me, but otherwise we cover the worst case regret. So we don't assume in advance that this environment has any good structure. We don't know, maybe this post-action context is just like useless. The domain expert told me to take some measurements. They are completely unrelated to what I did. It's possible. I don't want to rely on the assumption that it actually works. I want to verify it. So we want to exploit the structure if it's there. Still do as best as possible if it doesn't hold. We don't know in advance in which world we're in. This is the general idea of adaptivity. When we can expect that this post-action context would help. Remember the example of diabetes and blood sugar levels. Like, in the end of the day, it doesn't matter what you give me. If I passed a certain threshold, then it was effective, otherwise it's not. It doesn't really matter which action caused this blood sugar level. In some sense, two actions that have the same outcome on the post-action context are the same for me. You can think about Z as a low-dimensional summary of the experiment. And this is only meaningful if this space is much smaller. The post-action context is much smaller than the set of actions. So this model is only useful if I have 1,000 drugs, but the measurements, it may be a binary signal. Okay, this is high level. I'm going to formalize it, but it's the general goal.
At this high level, I'm a little confused about how it's different from just the loss. Because I mean, in the same sense, any two actions that have low loss are equally good. They both worked. So, I did, you know.
So the loss is only defined on the reward, yeah?
Right. So the Y versus this. So how is this context different from going forward? How is the Z different from the Y? Right. So at this point, I don't see it yet, but you'll say.
I'm going to formalize what does it mean, but
right.
yeah, but I care about the Ys, and I hope that the Z are going to help me.
Yeah.
That's the goal.
I have a question. Is that two questions? First of all, maybe jumping ahead a little bit, but if Z is the size of Z equal to the size of A here, do you revert back to the classical guarantee, or do you make it worse?
So you're going to see. There's going to be some price. We're going to be able to adapt, but we're going to pay some price.
Okay,
so this is the punchline. That's going to be the punchline.
Yeah. So the second question is that, does it only hold when Z is finite?
We assume the set of actions is finite and the set of post-action contexts are finite. Yeah. The bound scales with the size of usually the size of the set.
Can it be extended to?
So there are many papers about infinite arm multi-arm bandits. Yeah, there are papers about that, but this is where I assume everything is finite. Okay, so there were papers that made some assumptions about the causal structure. Recently, Blair, Piloti, Limbo, Wang, and Dan Roy formalized exactly what should be the condition about the environment that should help me adapt. So what is an environment? Remember, it's a set of distributions over post-action context and rewards. When post-action context would be useful if the choice of action A doesn't actually affect the outcome if I condition on Z. This is if you're from causality or Bayesian networks, that's how you isolate the effect of one variable on the outcome. I think, Arvin, what bothers you is like, how can we do it in general? But we're going to need to make an assumption that we need to know the marginals over Z or approximation. I think that would answer your question. Okay, so the previous bullet was informal. How do you define it formally? So we say that environment is conditionally benign if for any action, the conditional distribution of y given z is a constant function given a. In other words, if I know the value of z, it doesn't matter what the action was. Okay? All the information lies in the measurement. If you're from causality and graphical models, you probably would think about it as separation. So you would say that z, the post-action context, separates the reward from the intervention. Okay, so in causality, there are no arms and actions, it's intervention. Okay? So that's how you're going to use it. Then the connection is that there is a beautiful theory of graphical models in causality developed by Yuda Perl. He got the Turing Award for that. A whole new language of understanding causality with graphical models. So you can think about the directed acyclic graph representing a causal structure of a set of random variables. Here are only 3. And then what we're thinking about roughly is d-separation. What is d-separation? Is a graphical criteria for conditional independence. So if I know the value of this guy, then it doesn't matter where I came from. And in Bayesian networks, the network is much more complex, and there are many other criteria. But this is a really simple example of d-separation. So for me, it's easier to understand this definition. But if you're from causality, probably that would be a natural language for you. Does it make sense? But so previous papers assumed you know the values of all the parents in some sense. This is like the most refined definition you could come up. It was a really nice paper at DRIPS. Okay. So known results without adaptivity. Now I don't care about adaptivity. The worst case result is square root of the size of the set of actions times t. Classical result, UCB algorithm, upper confidence bounds achieve that. By Auer, Cesa, Bianchi, Fisher. Also Thompson sampling, which is really used in practice, achieved that up to a log factor that was shown 10 years later. Okay, this is classical results. If we have a causal structure, and if we have a conditionally benign property, and we know the marginal distributions over the post-action context. I'm going to explain that in a second. This seems like a strong assumption. Then the optimal regret is going to scale with the size of z and not a. Okay, this is a paper from 2020. And this is an adaptation of the UCB algorithm to something called Causal UCB algorithm. Okay, how should we think about knowing the marginal distributions? We show that this is necessary, but let's think about it. Let's say I have a drug and I have clinical trials that tells me what is the effect on the blood sugar levels. So that's something I can test, okay, offline. I still don't know what is the relation between the blood sugar level to the reward. So in some sense, the way I think about knowing the marginals is I will collect offline data. I'm going to try these drugs before I'm going to give them to people. I will know the effect on the blood sugar level, but I still don't know what is the reward given the blood sugar level. Okay? This is the story I built myself in order to understand it. It seems like a strong assumption. We can have approximate knowledge of these marginals, and we're still fine. So we can collect offline data and use that marginals. And among other results, we showed that without this knowledge, you can't improve. So you must know something about the marginals. Otherwise, it was pretty surprising to me because I saw this model and it was introduced like 9 years ago or 8 years ago. And I haven't seen okay, they assume the marginals are known, but I haven't seen a result that says, okay, what happens if I don't know? I know that approximate marginals are fine. And then we actually show that you need to know something. If you don't know anything, there is nothing you can do.
What do you mean improved rates? It's just
okay, the improved rate is the scales with the size of z. versus the size of A. So this is going to be the game. Like Z is small and A is large. The truth rate is the size of Z.
So why can't you always just like run some algorithm which at the first step I guess in the first step you need to collect all the marginals, so you need to pay linear engineering.
Let's say you know the approximate marginal as an input.
Okay.
The thing we're going to see that this algorithm assumes you have causal structure. And if this algorithm completely fails if there is no causal structure, it has linear regret.
Right.
So the punchline would be, how should I adapt to the structure if it's there, or recover the worst case guarantee?
So the causal structure that you're referring to is the like DAG that you showed on the previous slide,
yes.
right? Okay.
That Y condition on Z. So yeah. What you said? Yeah.
And I guess another question, so for this causal structure result where you know the marginals, is like the algorithm there, like you compute some core set over the actions using the marginals, and then you play on these core set?
You're going to use the marginals, so you want to run UCB, but you don't want to try all actions. So in some sense, you're going to play aggregated UCB using these marginals. I can show you later how to. Like we're going to use these two algorithms as a black box.
Sure, yeah.
To find the best one of them. So in some sense, to this talk, UCB and causal UCB is not really necessary. I have a slide about it. What I will try to do is to get a master algorithm that gets these two as a black box and try to run them and find the best algorithm. Okay, this is having you look worried.
So, because I was originally worried that what about Z equals Y, but now what you're saying is, okay, if Z equals Y, you actually don't need to do anything, you're all done, right? So I guess so here what we're thinking is sort of imagining maybe that the actions live in some, it's almost like they live in the low dimensional space. It's not quite, but it's, you know for each action this distribution on this small set Z. And so it's just, but how that Z connects to Y, that's what you don't know.
Exactly. So that's why knowing the marginals still doesn't give you everything.
Yeah.
That's exactly what I think. So the intuition is that in the worst case, we will need to try any action. But if Z separates A from the loss, then we can block A if you're thinking about a graphical model. And again, it's only meaningful if the set of Z is much smaller than the set. And this is a hint of how the causal UCB works. It's like we share information from Z to learn about a bunch of actions at the same time. Let's say I have 10 actions that have the same effect on Z. Then I don't really need to try all these actions. I can just focus on this Z. So this is the low dimensional structure. Okay, so what are known results with adaptivity? Okay, UCB wasn't designed for a causal inference, so it doesn't achieve the optimal rate. More interestingly is that causal UCB completely fails if there is no causal assumption. So it's linear regret in T, doesn't learn anything. Okay, so Blair, Lingbo, and Dan constructed an algorithm they call hypothesis-tested adaptive CUCB. And what it does, it achieves the fast rate if there is low dimensional structure. But if we don't have the causal structure, then we get e to the 3/4. Okay, so it adapts. Like it learns if there is causal structure, it gets us something really good. If it's the worst case, it still converges, but it doesn't converge as the usual rate of square root of t. The most important part, we don't know in advance if the assumption holds or not. They also show that there is some adaptivity that is not achievable. So what they show is that any algorithm with the optimal rate in the worst case, for any algorithm like that, I can come up with an environment with causal structure such that you won't be able to fully adapt. Okay, so there is something interesting happening here. Like on the one hand, we know that we can adapt. But at the same time, we know that we cannot do as if we knew in advance in which environment we're in. So this is the picture. This summarizes everything. If it was too many text for it, too much words. This is what's happening. You have the classic UCB. It achieves square root of A of t. It doesn't matter in which environment we're in. We have causal UCB that gets the fast rate if there is a causal structure, but otherwise it completely fails. There is the new TTIC UCB by Blair, Lindbo, and Dan that gets this rate for the worst case and gets the optimal rate for there is causal structure. And this is the negative results that says, okay, you won't be able to be here. You won't be able to get the square root of ZT and square root of AT in advance. So optimal adaptivity is not possible without extra knowledge. But we don't know what it, okay, so this is the Pareto frontier. We don't know what's happening here. This is like unknown to us. And we will show how to, so we show how to solve it. And I think also the interesting part is how to take their algorithm and show that what the other algorithm does in high level in a more clever way. So this is the full picture. There is an algorithm that gets this set of possible rates. It's called dynamic balancing. And it can achieve the square root of ZT rate if there is causal structure. But in the worst case, there's going to be this ratio, okay, that we have to pay. And it's interesting because this ratio is exactly what makes the problem interesting, right? If this ratio is high, then there is meaning to the causal structure. But this is the best you can do if you don't know anything in advance. So this is the best of both worlds Pareto frontier of this problem. And I call this term here as the price of adaptivity. That's the way. Yeah.
So this is incomparable with the 2 to the 3/4, right? There could be settings.
True. Like you can come up with these. You can get this terms as a function of t. Okay. It's a good question. I'm not sure because I hide here. Okay, there. Probably.
Maybe there.
It is comparable. Like it hides here. So I think it is. This is going to be better anyway.
Okay. Okay.
There. That's a good question. Yeah, it scales with A, with Z. So this gives us the full picture of the problem. Okay, I should finish soon. So I'm just going to give you I think this is okay. These are the results. Now a new method for getting best of both worlds. Okay, I think this is interesting to understand, like to know, even if we're not thinking about our problem. So there was a really nice paper in 2017. It's called Corralling a Band of Bandit Algorithms. So imagine you're working in a big company and you have 10 different algorithms that was designed by different people to work under certain assumptions. And you say, okay, I don't know like which algorithm is better. I don't know anything about the environment. Can you come up with a master algorithm that combine all of this set of algorithms such that I'm going to perform as well as possible as the base algorithm as if it was run on its own? Okay. Really cool idea. It's called model selection with feedback. There is a lot of research about this idea. Some algorithms better than others in certain environments. This gives you some best of both worlds guarantee. What makes the problem hard is the bandit feedback. If we have full information, you can just run like simple algorithm like weighted majority, edge, multiplicative weights, same thing. Because you're going to observe, you effectively run all the algorithms at once. But that's not what you want, because if one algorithm ran, you don't know what would have happened if you used a different algorithm. Okay? And you might think that, okay, so don't use a full information algorithm, use just a bandit algorithm, X3. But it doesn't work either, because the arms are not static. Each algorithm has its internal state. So if you're gonna, like, initially it might look that you just use a bandit algorithm. But actually, no, it doesn't work. And there is a good reason why it doesn't work, because you need to make some assumptions for it to work. And just think about it as, maybe there is one algorithm that is doing really, really bad at the beginning of the game. It's doing like a bunch of like weird explorations, and then exploit completely and gets like a really good rate. The master algorithm, in some sense, will try to run this algorithm for a bit and then discard it completely without waiting to see the benefit of this algorithm. Okay? So they needed to make some assumption of, they call stability of the base algorithms, that it doesn't perform that way in order to achieve good guarantee. So in general, you cannot get that. You need to make some assumptions in the worst case. Okay?
Does it mean that the master, so basically you would have two base algorithm, one work very well in the causality and one work very well in the other case, and then the master algorithm would choose between them?
Yes, exactly. So the arms here, the base algorithms are not static in some sense, so that's why it's not solved by just
So just make sure I understand. So you're saying the base algorithms themselves, their performance, like the performance of algorithm I at time t, is not just a function of I and t, but it's also a function of how many times you've tried it before and when you tried it, because its current state is a function of those things.
Exactly.
Okay.
And that's how they start motivating their pair. Because you think, like, okay, I'm just going to write x3. And then you understand it's like much more, there are some subtleties. So yeah, this is a really beautiful idea. So I've learned the word corralling from this paper. So we're going to corral in two stochastic environments. That's basically our problem. So I'll do the algorithm by Blair, Limbo, and then corral. It gets two base algorithms, UCB and CUCB. Then what it does, it plays optimistically as if there is causal structure. Okay, and each time it makes like an hypothesis test to say, okay, is this really a causal structure or not? If there is no causal structure, at some point you're going to see that you're not getting the rate you're expecting from CUCB. So you're going to switch. This hypothesis test is going to fail. You're going to switch to UCB. So what happens is that if there is a causal structure, you're going to play CUCB, and you're going to be happy, and that's it. You're going to get the optimal rate. If there is no causal structure, you're going to play causal UCB. Even though there is no causal structure, you're going to figure it out at some point. And from this point, you're going to switch to UCB completely. So there is one hard switch. Okay? You play as if this is a nice... So think about it. If you have a set of algorithms, you can start, but the one that gets the best rate as if some assumption hold, and then you're gonna try it out and figure out if that's true. Otherwise, you're gonna switch to a different algorithm. But there is a hard switch, okay? And this hard switch gets you this t to the 3/4 because you can do something smarter. Okay? So this is a simple way, and this is, I think, by the way, the first idea that was presented in the Best of Both Worlds algorithms from 2012. Hypothesis test, like run one algorithm, optimistic, like act as if like you're in a good environment. If you figure out at some point that you're not, switch. What dynamic balancing would do? So the general framework was by these guys, and we figure out that we can use it and like analyze it in the case of causal structure. I'm just going to give you the high-level idea. So that's the picture I imagine. In the causal UCB and UCB, I play the causal UCB. If this is not the right rate, I switch. What I'm going to do here is I'm going to have a balancing scheme. I'm going to play both algorithms equally. Okay, they're both going to get some regret. At some point, if there is no causal structure, then one algorithm, the regret of the CUCB, is going to be much larger than the UCB. If that will happen, I'm going to deactivate the CUCB. So instead of just running one algorithm and then switch, I'm going to run them in parallel, try to get them like this approximately equal regret. And if at some point one is performing much better than other, it means that the assumption doesn't hold, and I'm going to work only with the good algorithm. So there's going to be a deactivation step. Okay, so I'm going to play much less the CUCB if there is no causal structure. Okay, so this is the idea, and that's what's going to give you the optimal rate. In their paper, they say, okay, sometimes it doesn't give me the optimal rate, and we showed that there is a good reason for that, because we can construct a lower bound that shows that there is some price that you cannot avoid. This, in our case, is this ratio. I want to keep talking about the second paper. What's the message? This is a really nice topic in my opinion, adaptivity, best of both worlds, instance optimality, and these ideas. And the other message is that causal inference is used in sequential decision making, and actually a lot checking like the causal understanding of LLMs. There's people from Google DeepMind that are looking at that. So if you care about these things, just yes, okay. And we're gonna keep talking about a second paper. Okay, so it's going to be also about bandits, but this is a different question. So a context switch. This is by a paper with Alex and okay. And Alex led this paper. So okay, now we're going to have multi-arm bandits, but we're going to have delays. So now we're going to have a stream of incoming information. And let's say now we're going to have AI models that gives diagnose and treatment. Okay, so I'm going to try this AI model on a patient. And I'm going to have a doctor that reviews this treatment and going to give me a feedback. But this is a complex process, so I'm going to get the feedback in some delay. Okay, so this is called the multi-arm bandits with delay. The goal is similar, just to introduce delays, many applications. Challenges, there was the challenge of bandit feedback. Now we have an additional challenge. There are going to be delay in our feedback. So we should, we don't know, like at some point we took an action, we don't know the feedback, but we should keep making decisions. Okay, so this is multi-arm bandits with delays. We asked the question, what happens if you don't have an infinite pool of doctors? Like sometimes you're going to make a decision. Whether I want to test actually this model on a patient or not. And if I have T rounds, then a priori I will need to have T doctors. Is that actually what I need? That's the question, okay? So some cases will not be reviewed. And there are two questions. How we should assign, I'm going to call it schedule because it's going to be a scheduling problem. How I'm going to schedule the physicians. And the main question that we were interested in is, I want our regret to scale with the size of physicians. And then I want to find the optimal set of physicians I need in order to recover the same performance as if I have an unlimited physician. Okay, so I'm going to have a result that scales with the number of physicians. And from that bound, I can recover the optimal set of physicians to achieve the performance as if there are no limitations. Okay? Is the motivation clear? Okay. So we know what are multi-arm bandits already. So now we're going to have adversarial multi-arm bandits. The reward are not going to be drawn from a distribution. An adversary is going to pick in advance losses for the entire sequential game. And the adversary is going to pick also delays, DT. Okay, so it was YT before, now it's LT. And the difference is that here it's adversarial. So it's for any sequence. Then there are going to be some differences for every round. If the framework is what we call clairvoyant, then the learner observes the delay, DT. Okay? The learner takes an actions, incurs a loss, but you don't observe the loss. To observe that round T plus DT. So you suffer some loss, but you don't know, you will know only in the future this loss. And then for all previous rounds whose delay was expired, then you're going to observe this past round with the associated loss. Okay, so this is the framework of multi-arm bandits with delay. The new things that were introduced here is that first of all, it's an adversarial model. There's a distribution over the losses. And there are delays. These are the two changes. Okay. there are many variants of multi-arm bandit with delays. Sometimes we know the delay at action time, sometimes we don't. The delays can be fixed for every round. They can be round dependent. We're talking about adversarial delays, but there are many variants about this problem. For example, arm dependent delay, stochastic delay. There are hundreds of papers about that. Okay, so let's see our model with the capacity constraint. So now the learner has a tracking set S of size C. Again, sometimes we observe the delay, sometimes not. So if the framework is clairvoyant, we observe that. Then the learner takes an action, incurs a loss, but now there is no guarantee that we're going to observe this loss. If we want to observe this loss, we need to track this round in our tracking set. So we may add this round, this case, to our tracking set, as long as this set is not full. Again, if a previous round, if the delay was expired and this round was in our tracking set, then we're going to observe this round and the associated loss. And another change is now we have a tracking set, so we can ask about preemption. What is preemption? Is whether the learner can remove some previous rounds from the tracking set. Or maybe we can commit, like if we started to review, we cannot stop the process. If we gave the shot to the patient, maybe we already did what we need, so we need to complete the process. Okay, so we have multi-arm bandits with delays. Now we're not going to observe all feedbacks. If you want to observe some feedback, we need to track it. But the tracking set is limited. Does it make sense? I feel like maybe the context switch is too... Okay. Okay. So now we have more variants because we have the tracking set. So again, delay may announce that action times or not. Now we have the preemption assumption. So sometimes the learner may stop tracking rounds before receiving feedback, sometimes not. We have results for both full information and bandit feedback. I'm going to present the bandit feedback results. Main question, what should be C such that I'm gonna get the same bounds as if I have unlimited capacity? I'm not limited with how many doctors I have. Okay. So we took inspiration from ideas in TCS. One of them is online job scheduling. So we talked with Alan Borodin from, he had a bunch of results about this topic. We liked our model. So what are job scheduling? Jobs arrive sequentially. Each job has duration, how long it takes to perform the job, and weight, how important it is. We can schedule jobs to workers. So you can think about operating system where we want to perform some tasks. The objective is to maximize the total weight of the completed jobs. Another example is streaming. I will skip that. Okay. What's our main principle is to create a framework where we're going to separate the behavior of the scheduler from the learning algorithm. Okay, so the scheduler is gonna choose rounds to track without using the actions and the losses taken by the algorithm. Okay, so what the scheduler does is decides possibly randomly whether to add a round to the tracking set. If this delay expired, we send the feedback to the learner, and if it's preemptive, we can decide to remove these rounds from the tracking set. The scheduler does not rely on actions taken by the learning algorithm, and the learning algorithm depends only on the randomness of the scheduler up to round t minus 1. So we take an action at round t without knowing if this round is going to be tracked by the scheduler. And that allows us to focus mainly on scheduler and use known learning algorithms where we need to adapt some of their guarantees, but mostly I'm going to focus on schedulers. Okay, so I will tell you maybe just this result about fixed delays. So we have fixed delays D. So each round has a fixed delay D. It's announced at action times. This is the known rate for this problem. So pay attention to this D in the regret bound. Trivial observation, if the C is of size D plus 1, then we're going to observe all feedbacks. So what is the question? Can we do better? And if we couldn't do better, it was unfortunate. Probably wouldn't write the paper. But we can do better. So this is the optimal regret, and this is the additional term arises from the limited capacity C. And if you do the math, you see that the optimal capacity is the minimum of the number of actions and the delay size. So if the number of actions is much smaller than the delay, you can do much better than D plus 1. Clairvoyance is given, and we show that preemption is not crucial for obtaining the optimal result. How much time do I have, average?
2 or 3 minutes.
2 or 3. Okay, so I'm going to skip the algorithmic idea. So now every setup is going to have a based on some idea of scheduling. So the idea of scheduling here is batch partitioning. I'm going to skip that. Okay. More advanced setting, the delays are round dependent. We're in a setting which is clairvoyant. The DT is announced the action time, but it's non-preemptive. If we started to track something, we must finish the job. We have similar results, but now we have capital D, which is the sum of all delays. This is our result, where the term in red is the new factor into the limited capacity. And if you look at optimal C, then we got exactly what we got before with additional log capital T term, which is maybe not surprising because the delay is depending on T, but we don't know whether we can remove this log T. So basically we got the same results as in fixed delays with additional log T term. Usually in these type of problems, logarithmic in the horizon is fine. Like we're okay with these results. But it's an open problem if we can remove that. I'm not going to tell you about it, but there is a scheduler based on sampling from Bernoulli distribution. And we have also really similar results, but the delays are not announced at action time. So you don't know, you're going to deal with delays you're not aware of. But I allow you to preempt. So some rounds might be, you can stop tracking some rounds. And we get a similar result up to this term. And that's it. So too bad that I can't tell you about the scheduling ideas, but this is another cool idea of sampling delays. I don't know the delays. I'm going to sample proxy delays. And if I'm going to sample it well, I will be able to get the results. So this is really cool idea that I've never seen this idea. We call it proxy delays, and we sample from the Pareto distribution. So yeah, that's it. There are many variants of multi-arm bandit with delays. Limiting the capacity is really relevant in any one of them. Maybe contextual bandit, arm-dependent delays. I expect to see many applications of that. There are some gaps in our bounds. But yeah, all of time. That's it.
I have a question on the first talk. So the dynamic rebalancing algorithm which you use, does that also have some assumptions for it to work? Like correlating needs some stability assumptions. So dynamic rebalancing ensures that the regret is the same between the two sub-based algorithms. Now,
in their paper, they say they need mild assumptions. I don't remember any assumption that we needed to make to get this result. So, for my concern, there are no
Or
assumptions.
maybe the other way of phrasing this is like what properties of UCB and CUCB are used in
It's a good
ensuring that
question.
dynamic.
It's a good question. Yeah, I'm not sure about it. They need to make some mild assumptions. It's much more reasonable assumptions than in the worst case where we needed to assume that each algorithm is stable in some sense. But yeah, we should look at it together. Yeah, we can talk about it in lunch.
And so actually connecting what we talked about and your work. So I wonder, so in the model you talked about the first, back to the first half, so you assume that the mapping from actions, from the A to the Z is, that this, given you play the action is you understand the distribution on the Z. One way that maybe that could be learned is if you have a world where maybe you're trying to figure out the best drug for a variety of conditions, right? And so you have like a bunch of bandit problems, but they're happening either in parallel or one after the other. And so in some sense, this drug has some effect on the body, and that effect on the body is, has some effect on whether it's a good treatment for this disease or not. And so like you play, you pull the arm, you find out what it does to Z, you find out what it does for the loss for that problem, and then for the next, maybe you have another disease you're trying to figure out, but you're getting a little bit more information over time about that first part, and maybe that first stage is, could be useful. It's like a learning a pre-trained model for multiple different kind of, then you have the fine tuning for different.
What you say, I think if I understand correctly, you take measurements for one problem, but actually these measurements can be used in many other problems. So you used one drug, and maybe you can use this information in other clinical trials.
Yeah, like perhaps the Z part isn't affected, if that is common. I wonder if that makes any sense.
I think it does make sense. If this measurement, there are many measurements that are relevant to many things. So if you know something about the marginal, and there should be some connection, I guess. Yeah, I think it makes sense.
All right, thanks again.